probably day one because morning really the first day because last Tuesday was really day zero of the orientation. So we'll be covering a number of things here. I just put understanding distance as a place. I mean, those on Webex, can you hear me?
Yes, I can hear you. Hi Mohan, we can hear you. We are the FEM students.
So, this is what I'll be doing today. There will be some disclaimers. It's a kind of hands-on thing for those of you who don't know LaTeX, and we'll be covering a bit of SV also. And then there's a lot of statistics for which I didn't take action. This is not all. Start from the disclaimers. One problem I faced is I basically work on Linux, and Cisco Webex doesn't really work on Linux. So I'm using Windows today, and it's rather unique in this limitation actually. Most of the web conferencing software do work on Linux. Basically I'm not comfortable with this, and there could be some fumbles. Alright. I mean, it generally works, I've tested it. I will probably be able to compile my text sources. So, I mean, we are just having this discussion with Kinchan. Basically, it's good to use some kind of, I mean, it's not good to use R directly. That, what I mean is, I'll be doing this slide. It's not good to directly type into this, actually. You can use some or the other editor. And that's what I'm basically talking about. That all these softwares are limited. Basically that R GUI that you look at, that red thing that you type in, it's not a very good editor actually. What these guys did was they built basically the R program, and that's just one interface to it. So it's good to use some kind of text editor always. It will help you essentially, and that's what this is. That basically all programs are limited, and I mean the better a text editor, the more use you can make of your program. And those who are familiar with programming will probably already know this. And there are a lot of advantages basically. You can edit your commands, you can send them back and forth interactively. There are lots of other things. You can allow access to other programs. For example, there may be a spell checker or there may be a syntax highlighter, which is another program essentially. And this is what I use. You are free to use anything. Basically, I use Emacs, but I don't have Emacs today because Emacs works only on Linux. But yes, Emacs is a good text editor to learn, and if you actually have access to it, you should try to learn it. On Windows, you can use a lot of things. On Windows, I use WinR, although I don't have WinR today. I'll be using Notepad++. You can use RStudio. RStudio has one limitation: you can just draw one graph at a time. Whenever you draw another graph, it gets over it. That's not good. No, all of these are free. This WinR is free. In fact, all of these were with an WinR or Notepad++. Each of these is free. You can basically mix and match. You can try out 3 or 4 of them and see what works for you. So, I'll be doing LaTeX now. So, if you have LaTeX on your computer, you can actually try and compile a LaTeX program and see how SV works with it. Most of you may be already familiar with it. Are you familiar with LaTeX? So, this is how essentially this is how LaTeX looks. You start off with, in fact this is the code for my presentation today. So you start off from some document class, and if you want we can do a hands-on thing. I can type out a LaTeX program and you can just type it out if you have LaTeX program. Okay. So this is how it works. It's fairly simple. So minimal program would be something like you can follow along if you want to. Essentially, this is a minimal LaTeX document you can essentially use. So essentially, that's what I've used here. If I scroll down, it's a fairly simple system. You see, whatever I type here is what you see there. Whatever I type there is what you see in the slide. So there is no real syntax involved. And the only catch is that a line break is actually you have to leave a line in between, something like this. Leave a line in between. And the advantage is that you can actually comment out that line and essentially that's what the line break is. And mass formatting is probably the biggest advantage of this system. You can usually have mathematics formatting. For example, you see, it's exactly what I write here is what comes out there. And if I put anything in the dollar symbols, that's how it's interpreted. So it's bar x, so it writes x bar. And I say sum, so it says sigma. I say frac, so it puts fraction, and then in the first bracket I write xi, so it says xi, and then in the second bracket I write n. And if I use double dollar, it comes out on a line output, even though it's only the same. And you can number your equations, something like this. Essentially, if you want to number your equations, you use this begin equation and end equation. It's essentially the same expression each time, but whatever you put before and after it is how it's formatted.
How did you convert the LaTeX to PDF?
There's a program called PDF LaTeX, or you can simply use LaTeX. Okay. There's a program. So essentially, if I want to convert this, I have this. This is TextWorks. This is an editor called TextWorks. Okay. And I can select a lot of options here.
Right.
So I simply say PDF LaTeX, and then I say it will start compiling. Okay. It will take some time because it's a fairly long program. But I can compile the other one. I'll try it. Compiled it. That's the output. Because I didn't write anything new. So that's a very, that's all, in fact, that's how you can compose any document. If you want a title, you can put a title.
you have a document for the basic syntax?
You can get them on the internet. I just thought that you might want to follow around. So. Fairly simple, actually. That's all that you need to. The advantage of using LaTeX is because all these spaces, it looks professional looking. Whenever you use LaTeX, it looks professional looking because it's not like Word. In Word, you put all these spaces and tabs and so on. LaTeX has all these pre-programmed. So people who have done this, they have actually found out the optimal number of spaces and tab breaks and so on. It looks professional. And it's fairly easy to use that. It's much easier to use actually than Word. We'll come to that. And you already know this is bold text and so on, so I'll show you the code for it. So essentially when you say XBF, there, XBF, this comes as bold text. When you say it's XIT, when you say XIT, it puts it like that. When you put text PT, that's typewriter font reader. So it comes like that. And this typewriter font is essentially used for computer terms like AR, or if you want to have some code, you use that. That's what it is. S-Weave I'll come back to later. Essentially I'll be doing S-Weave throughout this. So this is just a short introduction. The mean, we already saw the formula for the mean is essentially you sum up all the numbers and you divide by the number of figures. Now, the mean is that's what I was talking about in the last class, that there are alternatives to each of these actually. This is just one statistic. Statistic is, of course, if you have a sample, whatever sample you have, and each of these x's may be a scalar or a vector. For example, if you have the weights of 40 people, that will be 40 numbers for you. That constitutes the sample. Or if you have weights and heights, that is actually a vector for each individual. So that's your sample. Any function that you compute, whether you add these up, whether you take the maximum, whether you take the minimum, even if you, in fact, if you just simply sort them, that constitutes a function of these sample values. And any function that you have, that's essentially called a statistic. That's just a terminology that we use. So any function of the sample values we call a statistic. So when I say that the mean is just one statistic in a wider class, that mean is a function of the sample values essentially. That's why I'm calling it a statistic. And that wider class is what we call location measures. And we'll see what location measures are. The idea behind location measures is that one, it should be a single number, and two, it should represent the typical value essentially in the data set. And that's the obvious problem, that there may not be such a number. But how will we know whether such a number exists or not is not what we'll cover today. We will cover it next time. So right now we just assume that there is such a single number that represents a typical value in the data set. So question obviously is, I say typical, but what is typical essentially? Because that's a English language term and it can have a number of different meanings actually, depending upon the context. Synonyms are common, unremarkable, indicative. So you can in fact use any of them. You can use common or unremarkable or indicative. I'll basically try to use that indicative one. And I will not, I'll ask you to translate it into mathematics. And this is what most of statistics is about. Because we use some English language term, for example, we use dependence and then we translate that into relation. So we just do that a lot of times. We just take some English language term and we try to translate it into mathematics. So right now I'll try to, in fact I'll ask you to translate typical into mathematics. So, that's question time. What do you think could be used to measure the typicality of a number? To make it simple, I can put down some numbers here. For example, say suppose I put down these 5 numbers there. What do you think would be a typical value and how do you get it? Because we'll be doing this a lot actually later on. We're doing this right now because it's simple. A location measure is a very simple thing. You have just simple univariate numbers there and you would want a typical value. So forget about the mean. How would you arrive at a typical value? For example, if somebody asks you, how did you arrive at this number? What would you say? I mean, you can just put anything out there. You can have a discussion. And that's my right answer. Okay, those are actual, okay, but why do you call them typical values? There must be some underlying basis for it, right? How? Typical impedance is just like you're passing the ball from one to the other. Think in terms of something that you can measure.
Mohit, we are not able to see the numbers. We can read out the numbers.
Okay. Can you see them now? The numbers that I wrote were 31, 37, 42, 51 and 28.
Okay. Yeah, now we can see them.
Essentially, I have these 5 numbers here, and basically it's just you can in fact forget about this stuff right now. We'll come to this later. Somebody gave you 5 numbers, and what would you say a typical number is? Just some concept, some kind of idea.
The nearest 10 and take the highest frequency.
Okay. So one option that I just put it like that's one option. So take modulus 10 would essentially be what you said. If you take modulus 10, you would get 3, 4, 5 and 2. And then you would take the most common one of them and multiply it back by 10. So, what does it give you? For example, here, if I do that procedure, I would get 3. And of course, 3 is the most common, so I say 30 is my typical value. Why do you think 30 would be a typical value? I mean, what underlies this procedure?
Possibly the frequency with this 30 has come up.
Okay. One idea is frequency. Okay, let's run this frequency. Suppose this first digit 3 was the most common. What does it make it? I mean, it's obviously the most popular choice, but doesn't it make it close to the other numbers? then you give the most frequent choice. Is it not closer to the other numbers than something else? For example, I say some arbitrary number, say 100 or 70. Is not 30 closer to these numbers than these? So let's take that as a guiding principle. I mean, is everybody convinced? Or do I have more suggestions?
130 is not close, because if the sample would be like 31, 37, 100, 150, if the numbers would have been that, then 100 would be...
No, just for this sample. So suppose, okay, we take your sample also. For example, what's the sample?
Suppose, like for the example that you showed that 170 would not be the number. Like if the sample would be 31, 37, 100, 70, and say 40.
Okay.
Then 30 would not be the closest representing the sample.
Okay. But, of course, this procedure would then fail. That's why I'm not talking about procedures essentially. I'm asking you what guiding principle would you have? I mean, of course, none of these three always work, actually, is what I was in fact shown. And of course, this is just another procedure like that. But the point is about guiding principles. I mean, I'm not saying that this algorithm is my guiding principle. What would be the guiding principle essentially?
The number that will be the closest representative of all the numbers.
Yeah, I mean,
the
closest representative are, you can drop one of them, they're super close. So which one will you drop?
Dropping closest.
Drop the other one. So essentially the idea is that this is something like representative. So, okay, I'll just tell you. The idea of typical is similar. I mean, we can all agree on that. It should be similar to all the other numbers. And when is a number similar to others? That's a simplification that I'm offering you. Typicality would mean some kind of similarity, right? So when would you say one number is similar to others?
And we can represent the other numbers by this particular number.
It's trying then. I mean, that is division algorithm. Obviously.
Not actually representing, means not like a multiple of that. Something like even a prime number can be represented by suppose 2x plus 1. Like a sort of representation I'm telling.
Okay. Any other? So when would you call a number similar to others? So let me give you an example. Is 30 similar to 31 or is 30 similar to 100, say 90? But 31 is a prime number and 90 divides by 3 exactly. Ignore a minute.
It depends.
No. Okay. Of course 30 is similar to 31, yeah. So let's say 30 is similar to 90. Essentially that's what it is. So, see, if numbers confuse, you can take them like weights. If I weigh say 61 and somebody weighs 60, our weights are close together. You would be similar. You can actually, or if I buy 5 kgs of tomatoes and you buy 4 kgs, we are similar. If somebody buys 100 kgs, he's quite dissimilar to me. So it's not mathematics, it's just basic, some kind of physical concept you can relate it with. We're not talking mathematics. Statistics is all about physical concepts. So essentially, a number would be similar to others if it's close to them. If you can take it for any kind of measure, say weight, height, or something else, say marks. So each number, numbers are of course abstract concepts, but they represent some physical quantities. And they're physical quantities that we are trying to talk about. So 5 in itself may be meaningless, but 5 kgs is meaningful, and 5 kgs is always similar to 4 kgs. So that's what I am going to do. Distance. That's the underlying concept. Distance. When it becomes mathematical, you can just ignore it. I mean, if you know maths, you can read it up. So essentially, it's distance. So I'm going to hand it over to you. I mean, what constitutes distance is the question. So So mathematicians have already studied it. I'll give you the definition really. If you want, you can check it up. So if we are confused by d-dimensional space RD, we can just say that U, V and W are just three numbers. It's 4, 5 and 6 essentially. So just three numbers. And D is some function which takes just two numbers at a time. And what I say is it should always be greater than equal to 0. Because distance is positive always. So for the time being, you can think of this as some kind of geography. So what I'm saying is I want to have the distance between Hyderabad and Vizag. And I say that that distance, whatever I say, should be positive. And the other thing is that it should be 0 if and only if U is equal to 0. So the distance from me to me should always be 0. And that's just common sense conditions that I'm putting in. And distance from U to V should be the distance as V to U. And distance from U to V, this is essentially the triangle inequality. It's basically the point is that you can get it. You can get it from the bisection of the line, actually. If you bisect a line at any point, you'll actually have exact equality. And whenever you have two dimensions, you don't have exact equality. Essentially, why I'm putting this is that till here, in the last slide, I was essentially talking about English. But when I start translating it into mathematics, I need some exactness. For example, if I have a function, say sin x, and if I have another function, say x plus y, and if I have another function, say x square minus y square, I should be able to tell which is a distance and which is not a distance. That's why it's important to me, this definition. Because in English we can say anything, but in maths we have to be exact. And in fact we'll be translating English from maths, essentially. So that's why I need this definition. I need exactness. For example, according to this definition, I can say that, say, x minus y is not a distance function. Because x minus y can be negative. And, say, absolute of x minus y can be a distance function. So that's always positive. Or, say, x divided by y cannot be a distance function. Because even if x and y both are positive, x by y is not the same as y by x, which violates the second condition. So I'm essentially just translating my common sense things into maths. And then I'll see how we can use that. These are the most commonly used distances. These are called square distances. That d of xy, dx minus y whole square. That's your most common distance. In fact, this is the distance metric that you are using in all of statistics. Your OLS and just about anything that you have learned probably till now is based on this metric. So it's just x minus y square, and you can actually verify that all of these conditions hold true. Because it's a squared thing, so even if you get a negative number by subtracting x minus y, it will still be positive. And it's 0 only when x equal to y. You have that symmetry. Distance of x equal to x from y to the same as y to x. And you can actually prove that. That's quite simple. That last condition of the triangle inequality is fairly simple. Actually. You can just add and subtract z, and there is a typo there. It should actually be y minus z here. And you can prove it. This is basically this comes with a minus sign. So it's just like x minus y whole square again. So just expanded by terms. So x square, y square, and then minus 2. So because this is negative, this will always be, because this has something added to it. So it can at most be equal, but it will generally be less. And that's exactly what your dx z plus dz y. So let's see what I can get with it. So what I want to say is, how does this, okay, I put this dxy there. Dxy is x minus y square. How does it look, essentially? And what we'll essentially be talking about later is if it's a good distance at all. Or when is it a good distance. And because distance does not always remain constant, you see, even in the physical world. Because if you want to go from Hyderabad to Vizag, you can go by train or by, say, road, or you can go by flight. And each of these will take a different route. You can actually choose the distance. It doesn't remain the same always. And say if you want to go from India to North Pole, you can't go in a straight line because there are high mountains in the way. We'll have to take some route. So distance even in the physical world is not the same essentially. And it's the same with numbers. The distance between two numbers is not always the same. And we'll come to that later actually. So that's why I'm trying to discuss this distance function, because it's the most common distance function. You have been using it, even though you may not know it. You've been using this for OLS, you've been using this for mean, and for just about every statistical function that you ever computed. This was the distance that was actually named. So let's take some point, say 30, and the question is how far are other points from it. And I'm going to use the same square distance as my distance function. So this is R, so basically I'll be mixing up R with my stats. R is the language that I'll be using to express this. So first I assign the value, say x, and that's the assignment operator. You can use equal to, but it doesn't always work, so that's the assignment operator. It's the less than symbol and then a dash. That's how you assign values. That's x 30. And then I can find the distance of that point from any other. So what I've done is, so if you want to know SV, I'll wait here and I'll show you what SV is. One very common problem that you guys face is that you do some analysis and then you have to copy paste the results of that analysis into some document. So that's why I introduced LaTeX, because with LaTeX you don't actually have to do that. That's what you do. This begin frame and end frame, so you can just read it from this line to this line. In fact, the full frame, essentially. So just start from the begin frame. So this is my slide. So this is how I do it. So when I want to write something in R, I just write it directly in my LaTeX document. And when I have to write it, I use these two less than signs and two greater than signs. And then I say equal to. And then I say x. This is just R code directly. So this is the LaTeX document. And that LaTeX document, anywhere I can put this block. So the block is essentially two less than signs, two greater than signs. So the block is essentially this. Within that block I can introduce anywhere in my LaTeX document. So the advantage is I can just write my report, and wherever I have, say, suppose I want to find the mean, or suppose I want to run a regression, I can just put the R code directly here. And when I compile it, this is how it comes. So it will give you the result as well. So it gives you the code, and it gives you the result. So when x is assigned the value 30, there is no output. But when I say something like x minus 30 whole square, then there is an output, and that's how it comes. So what actually happens is, I start from this document, then I essentially go to R. I say this is my LaTeX document. In fact, this is the source code for these slides. This is the LaTeX document. But when I put these symbols in it, these symbols like these, when I put in it, then I have to name it .rnw. So instead of calling it .text, it's actually classed as .rnw. NW is basically there's another function, there's another program here actually, noweb, which will actually compile these two, but you don't need to know that. So I go to R, I say retrieve the file name, and what it will do is it will go through the entire file. What it does is it goes through the entire file and processes each chunk actually, and that's what it has done. And what it outputs is a file like this. So you see, I just wrote x minus, so what I wrote was this, which is fairly simple. And what the program did was it translated it into something like this. It's fairly long and I don't actually have to see it. And then I can simply compile it like an ordinary text document. So what Xweave allows me to do is I can mix my code with my analysis. So each time I say something and then I can do it. And then I don't actually have to bother too much about what will happen. So let's come back. So essentially I assign the values, say 30, and then I can find the distances. So it's, so for example, if I want to find the distance from 20, I say x minus 20 whole square, and that's 100. Or x minus 40 whole square, that's also 100. So it's just in fact something that you can see from the control. Or x minus 1, so this is the distance of the point 1 from 30, this is 41. And this is the distance of the point 30 from itself. Now, what I have done here is I computed the value of this function x minus y whole square at some single point. But computing the value of any function at a single point is seldom meaningful, because what we want to do with any function is that we want to see its behavior over a range. So if you compute it at a single value, you never get that kind of behavior. So what we should do is essentially look at a range of values. So you set some range, say 30 on the left side and 40 on the right side, and you compute the function over that range. This is what you do. And of course, this is what a graph shows. It's useful to draw graphs. Let's look at the graph of our distance. So I have R mixed up with my statistics. This is how I would define a function. This is how functions are defined in R essentially. So you put a symbol here, whatever you want to name your function, and then you put an assignment operator here. And this is kind of special function, so it's in fact called function. It's not a keyword. I pointed out there are no keywords in R. So this is a function, and then you say what arguments you have. So I have two arguments here, x and y. And it's x minus equals square. So very simple. The assignment operator is this function dot special function, and there are two arguments x and y. So I have used the same point that I used before. I have 20 here, I have 40 here, I have 1 here, I have 30 here. And it seems to work well, because 30 minus 20 is 10 and that's 100. So it seems to be working well. Now, suppose I want the graph of this function. So this is all the R part of it, essentially. So I want the graph of this function. So suppose I want the distance of the point at 30 to all points between 0 and 60. So how can we do that? Yes. This is another thing that I talked about last time, that R is a language that is slightly different from C. The thing is that it can accept C, it has C-like syntax. And you can write C in R, in fact you can write any language in any other language, but it's better to use R specifically. Essentially this is what you would be familiar with. So you define a vector of length 61, because all points from 0 to 60 would be, I'm taking only integers, because all points between 0 and 60 will be. So I take integers between 0 and 60, which are 61 integers. So I define a vector like that. It's a numeric vector of length 61. And then I use a for loop for I in 0 to 60. Distances of I is d30 to I. The R way of doing it is quite simple actually. That is all you need. So the SEQ function is actually sequence. Sequence generates integers between 0 and 60. Okay. I mean, if you don't follow, please ask me. Actually, part of this is teaching R on. So sequence is essentially the first argument is from, that is the next argument is 2. So it takes from equal to 0 and 2 equal to 60. And it will take integers by default.
I'm trying to do this. How to push back when I click backspace it doesn't go. When I click up, this thing comes in.
And what it does is it inserts a break like this. And you can actually write it.
No, right side.
No, that's from the So essentially what sequence does is it takes a from, it takes a 2. So it takes 0 and 60. So essentially what SEQ, so I can actually show you. That's what it does. You don't need to write a for loop anymore. So let's go back. This is sequence 0 to 60, which is this essentially. And then it says S apply. Now there is essentially there is a difference between the procedure. Procedural programming is something like this. You have a variable and then you say the operation for each element. That's what we are doing here. That's what a for loop is. You say that for each element do this, essentially. Now, in functional languages, that's not how it goes, actually. So what it does is this S apply, what it is saying is, this is the vector, this is a function D. This vector, apply this function D. So, essentially it's something like this. So, let me have a very simple function. Say, it's a function that takes a single argument and gives me the distance of any point from 30. Okay. The next is a set of points that I want distances from. So I can of course use a for loop. I can say for I equal to this, and for each point I can do that. Now what S apply does is, it takes the argument first, and then it takes the function. What S apply did was, it took each point from here, from X, and to each point X, it applied the function D. So what it did was, it took 0, then it said what is D of 0? D of 0 is 900. Then it said D of 1, 841, D of 2, 784, and so on. It's essentially doing the same thing, but we will see a lot of advantages of this, actually, as we go on. And it's also, I mean, the simplest advantage that you can see is it's less error prone, actually. You can hardly make an error with it. Because you see, suppose you want distances from say 62 points now. You have to change 62 at 2 places, here and here. But you don't actually have to change it only once here. And that's what a lot of program bugs are actually. If you have ever read the news, all these vulnerabilities in Windows and so on, this buffer overflow and so on, that's what it is essentially. That people change it here, but they forget to change it there. But there's no problem like that here. And it's easier to read because for loops and so on, I mean, if there are multiple lines here, it will be hard for you to figure out what's going on. But once you have a function like D, you just have to read the D once, and then that D itself is applied to each argument. That's what it is. And that final argument that I have to pass as 30 is because my D was originally a function of 2 arguments. So S apply will only give it one set of arguments. And the other set of arguments are passed it using 30. So it's essentially D of this and 30. It's a fairly neat way of doing things. And you get used to it as you go along. It's a fairly neat way of doing things. And there is a whole family of apply functions. Actually, these are called apply functions. Apply is the simplest. It is in fact simplify and apply. And there's a function called apply. There's a function called lapply. There's a function called mapply, papply. So they each do slightly different things. It's helpful. And in fact, another thing that you'll notice is if you write this in R and if you write this in R, there will be a speed difference. For small numbers, you'll not see it because this is just 60. Try it with 600, you'll actually see the difference. Because R externally is this. And this is just something that R will also execute but not very happily. So there's actually a speed difference. If you use the apply functions or if you use some other constructs that are there in R, it works faster. Now that we have our distances, this is how we plot. So the plotting function in R is simply called plot. You simply say plot and whatever your vector is. So my vector here was distances in each of these cases. So I simply say plot distances. Type equal to L, this is L, it might look like 1. Type equal to L means that plot it like a line. If I say plot equal to P, then it will plot it like points. I can show you. By default, it's plot type equal to P. That's what it is. And type equal to P is only useful if you have actual data. Here we are not really concerned about these particular points. What we are concerned about is the behavior of the function. So that's why we will use type equal to S. And the function behavior is easier to see that. So our small range is, here it was a very small range actually. So it was just from 0 to 10. For small ranges it looks kind of linear. It's not linear. And that's the basic problem. So for a large range, this is from 0 to 60. This is how it goes. Points that are very far from 30 this side have a fairly high distance. At 0 it's like 900 probably. And at 30 it is 0 obviously because 30 is at 0 distance. And then on the other side it increases. So the point to note is that one, it is symmetric, and the other thing it is kind of nonlinear. In fact, it is nonlinear, it's quadratic. Now if we have covered distances, how do we construct location measures out of it? Because essentially that's how from where we started. We had some 5 numbers and we said that the underlying principle is distance. So now we have a particular distance measure. How do we construct location measures out of it? It's fairly easy. It's actually just a 3-step process. Start with any distance measure. We already have a distance measure already. You hypothesize. You just say that I don't know what the location measure is for me right now, but let us say that it's mu. Find the distance of every point from mu. So for example, it will be 30 minus mu square. The distance of the point mu from 30. So find the distance of every point from mu. These will all be functions of mu actually. If you have n points, the distance of the first point will be d of x 30, which will be x1 minus 30 whole square. So these will be basically functions. You aggregate these distances from that. I'll not go much into this. The simplest aggregating function is simply take the mean. There can be other aggregating functions actually. So you actually have 2 things that you can change in any location measure. You can change the distance measure. The different distance measures will give you different location measures. And you can change the aggregation. The aggregation that we use is simply the mean. And then, because each of these di's is a function of mu, this big T will also be a function of mu. And then you minimize this function as a function of mu. So you find that value of mu which will minimize the aggregate distance. And that's what it is there also. you're taking a point mu that is closest to all these points. So you start with calculate, so you hypothesize that value to be mu. You find the value, you find the distance of that point to every other point. You sum them up, or you can take a mean. In fact, it's the same. You can just sum them up. And you minimize that as a function of mu. So what you end up with is a function that is a point that is closest to all the other points. But under this distance matrix, whatever it is. Different distance matrix will give you different locations. Let's see how it works. Let's say I have only 3 points, 31, 35 and 38. And what I'll do is you say that x, so R does not distinguish between scalars and vectors. Everything in R is a vector. Even if you have a scalar, R will call it a vector of length 1. So essentially this is a vector, so this is my sample. I say x is assigned a value of 31, 35 and 38. C is the vectorizing function. So I can't simply write 31, 35 and 38. I have to tell that this is a vector. So x is a vector which has the values 31, 35 and 38. Capital D is a function that will, so the distance of, so I will assume that my, I'll write it down. Actually simpler than this. In fact, you can, if you say, I was just telling you about SV, right? So you can not only get your document, you can actually get your R code separately also. So I said S triangle, and if I say S triangle, it will give me the R code separately. This is all the R code that I actually wrote in my presentation. It's fairly convenient software. Okay. So essentially this is what I did. I took started from here. So this is my smaller distance. It will give me the distance of any point from x, essentially. Now, notice one thing. Suppose this is an intricacy of R, and that's why R is so useful from a statistics work. So before I explain that, let me show you one thing. Say I say 30 and x. This actually becomes expression in y. You cannot evaluate it because it will give you an error. But essentially that's what I've done here. That becomes an expression. So what I have done is, I took the d here, which is actually a function of 2 arguments. And then I passed d only one argument each time. It was 31, 35 and 38. The other argument was undefined. And that I make as a function. So that's another sense of R that you can actually construct functions out of functions. That's why it's so commonly used in statistics. So D is actually a function of functions. So I can actually, so the advantage is that I can translate everything that I write in my presentation directly into. So this is how I write in mathematics, D of D1, D2, Dn. I can translate it exactly the same way into R. So I have D as a function of sum of D1, D2, Dn. So that's why the syntax is slightly uncommon, but it's really useful for mathematics. Because I can write exactly what I think. And trial values are just some values. I go from 20 to 42 and I go by 0.5. So it will generate 20, 20.5, 21, 21.5, something like that. And then I say plot. These are my y values I supply. Against, this is the tilde symbol I use for against. So y against x, this is my y, this is my x. And I want a line graph. I want the label on the x-axis as mean. So essentially these are trial values. I just don't know what my mean is. I'm trying out all values between 20 to 42. That's what I'm doing. Do you get it? Should I repeat? So basically I don't. So basically that's. So let me just come back to this. I started with a distance measure, which was d of x minus y whole square. And then I found the distance of that point from each, aggregated it, and I want to minimize it. Now I am on the last step, because this I know, d is x minus y whole square. I know the distance of that point from every other point. I can actually find that. I have my d, because that's just sum. And now I want this minimization. So what I'll do is, I'll take a sample as 31, 35, 38. I'll say that my capital D is, so this is already known for me, so it's sum of the distance of 31 to x, 35 to x, and 38 to x. And then I say that my location measure may lie somewhere between 20 and 42. I don't know. I'm just trying out somewhere. So what I just do is I take some trial values, and then at each of these trial values I compute this function D. And wherever it becomes minimum, that is my location measure. So mean is nothing really special. That's the theory behind it. So just a distance measure that you're aggregating, and then you're finding the point that is closest, all the points. And I'm taking 20 to 42 because I don't expect my location measure to lie somewhere near 100. So in fact, there's no problem. I could have extended the graph to 100 or 200 or 300. It doesn't matter. I just draw the graph. And what I see is that at points, so these are trial values. All of these could be possibly mu for me. I don't know. Each of these could be possibly the mean. So I don't know whether 25 is my mean or 20 is my mean or 50 is my mean or something like that. And what I do is I plot this function D against the trial values, and what I find is it comes almost to, in fact it's fairly near to 0 at somewhere near 36. That's my mean. And the usual formula for the mean is simply an explicit simplification of this problem. But the point is that when we do statistics computationally, we seldom have closed form solution. So when I say that x star, when I put down a formula like that, that formula is called a closed form solution. Because it's very simple, you just add up all the numbers and then you divide by n. But in statistics, we very rarely have closed form solution. So what we generally have to do is we have to draw a graph now. The graph is the more basic thing, and this is just a derivation. So essentially what we do is we just solve the problem explicitly and this is the solution. Sometimes you can't solve the problem. So that's why we have graphs. We can actually get the mean graphically by using this procedure. This is the same thing. So now that we have the mean, okay. Now this is the only data that I am going to use. In fact, I am not really going to use it much at all. This is Lake Huron. You can have that, and it comes with base R. You simply say data Lake Huron and it will give you the data. This is the time series measurements of Lake Huron is a lake in America. These are called the Great Lakes. These are 5 lakes. So this is the description. So there are 5 lakes. 5 huge lakes in America. What are these? There's lakes, Superior Lakes, so on. So Huron is one of those big lakes in American Canadian border. So from 1875 to 1972, they take annual measurements of that level of that lake, and that's lake here. It's 98 years. So for any real data, you can do the same thing. I just wanted to give you a real example because this is really small because it's just 3 numbers. So essentially you ask for the data and you put your D the same way. I use supply because you see, if I had put it like this, it would have become too long. So it makes my program shorter. So I simply say supply late Huron. So this is my data. For each number in late Huron, apply the function b, and the other point is x, which is unknown here. Because it's so when I say d of 40, it will give me the distance of the point 40 from every point in late Huron. That's what the idea is. In trial values, I take minimum value in late Huron and maximum value in late Huron. So somewhere in between my location measure should lie. That's the idea. And then I plot. So this is my y value. So I say apply over trial values the function d. That's essentially how I read it. So apply over this vector the function d against. So y against x is every plot is in fact y against x. So my y is this against trial values and type equal to L, so I want a line graph. The x label I want as new and the y label I want as t. And in fact the grid, you can't actually see it here because it's too faint. There is a grid. So this is what I see. So my minimum late Huron, I can actually get you some of these statistics. So the minimum value in late Huron is 576 feet and the maximum value was... Why am I getting an error?
Not getting error, I did not try to do that. What's the error? Probably function. Minimum is 576. Could you show us the contact on the site?
So basically the idea behind this graph was that you can get the mean graphically for any data set. And it's not very easy, not very difficult. In fact, this entire thing runs fairly quickly. So this is of course the mean. And we have of course gone deeper into the mean than ever before. The question is why? Why should we care actually? We already have a formula for it which is fairly simple, and all these graphs and all this technology is fairly complicated. Why should we care? So it's fairly simple. So the idea is that this is not the only location measure. There are a huge number of location measures, and essentially I start from, as I said, that you start from small d. The starting point is always small, which is a distance measure. So the idea is that there are alternate distance measures. In fact, there is an infinite variety of distance measures. So, in fact, if you want to construct a distance measure, it's fairly simple. You see? This is a distance measure. You multiply it.
Take a log.
Sure, this is a distance. Log should become negative. That would not be a distance measure. But you can multiply it with any number, and you can get a new distance measure. So there is nothing holy about this particular function. And in fact, what we can also show is each of these will also give you the mean. So you don't have to say that this is my thing. You can say that this is your distance measure. Each of these give you the same solution. And there are other distance measures actually. So there is an infinite variety of distance measures, and there is an infinite variety of location measures. I have still not said why should we care about them. Because distance measures are chosen by us. If I take same example of going from Hyderabad to Vizag, you choose the mode of transport. You choose to go by road, or you choose to go by plane, or you choose to go by train. You choose the thing. And you choose based on your time and convenience and so on, basically. And the same thing with data. So, based on the data, you choose the distance measure. It's not fixed, it's not God-given. So, essentially, each distance measure, because it's distance measure, and it's measuring what's near and what's far. So, we will have a belief, even without seeing the data, or after seeing the data, we'll have a belief on what is near and what is far, basically. So, or you can say that it's kind of penalty. Okay, to see points 2 and 3, this is the question that I pose. Suppose I believe, or I get the weights of say 40 people. Then if I expect these values to be closely packed, suppose all of them will be say around 40, then do I penalize more or less? Or if I expect our values to be loosely packed, do I penalize more? So to see the penalty, you can look at this. Can I erase this? So let me say that and let me say that somebody gave me this point. So let's say somebody gave me this point. This is a trial value. There's nothing special about it. I just say that maybe this is my location measure, maybe. Now, I can find the distance of this point to any other point. Okay. For example, the distance of the point 30 would be 25, and the distance of the point 32 would be none. Okay. Then finally what I'll do is I'll add up all these. And then I'll minimize. Okay. Is is essentially the procedure that I have. So I choose a trial value. I find the distance of that trial value from every other point. I sum up these distances, call it capital D, and then minimize this. Okay. So now look at this thing. Just X here and D. Now what my D would essentially be okay. So now this is like a penalty. Point T is not represented by its actual value. It's represented by this number 25. It's like a penalty that I'm putting on 30. And if the point is very far, for example, if the point is say 100, the penalty will be very big. So what would it be? Fairly big. And as the points go farther and farther, the penalty will keep increasing. But suppose I use this is x minus b square. So this penalty will not be so. So these are my points x. Suppose I use the absolute distance. This is also a distance because you can check up all the properties. This also satisfies. So essentially I'm choosing my penalty. I'm choosing whether I want to represent 30 by the value 25 or 5. Or I want to represent the value 100 by 4225 or 65. I can choose my penalty. So essentially choosing a distance metric is like choosing the penalty bit. That is what I was saying there. That distance metrics are basically like penalties. And whatever your sample may be, how far or how close these points are is what is measured by your small d. Let small d is like a penalty. So should I penalize 30 by a value of 25 or a value of 5? That's the question that I'm asking. So now the question is back to you. So if you expect your values to be closely packed, for example, if I never expect 100 here at all, if all I expect here are small numbers like 32, 30 and 32, numbers close to this, should I penalize more or should I penalize this? I mean, that's just the first part of my question. If values are closely packed, for example, all my numbers lie, say minimum is say 28 and say maximum is say 41, then I'll get penalties. Should these penalties be big or should these penalties be small? Because that's how you choose your location region. Your numbers are very closely packed together, so you expect them to be closely packed together, for example. Then, what would you say? All these numbers are very close together, essentially. So,
Penalize less.
huh?
Penalize less.
He says penalize less. Why?
They are closely packed, then there should not be much penalty, right?
That's just a statement, no? This is not a reason. Okay, your numbers are closely packed together. Okay, so do you expect a number that is very far away? So a number that is very far away, would that be very unusual or would that be all in a day's work kind of? Yeah. So, okay, let's just do it the other way around. Suppose the numbers are very loosely packed. Suppose all your numbers are between 30 and 35, but you have plenty of numbers beyond 100. And you have plenty of numbers beyond minus. It's something like, so if I could draw a number line, say 25% of my data is here, and there's a huge amount here and a huge amount here. Say, what would be, that would be 75, say it would be 40 and 35. And the distance is very big. My numbers are very loosely packed now. So now would I want my penalty to be big, or do I want my penalty to be small? Okay, let's take it back. You have all these penalties, right? Okay. So now when you construct a big D, okay. Now let us see the contribution of this faraway point 100. So it's essentially so that measures the contribution of my faraway point. This is the function that I'll be maximizing. So this is the contribution of this faraway point 100 on the full function. 25 plus 9 plus 4. I can actually get the values for you. So D1, when I use the squared metric, the faraway point is constituting almost 99% of the weight, actually. That's what you can see here. When I use 4225, that would be almost 99% of the weight. So when you maximize, say, D1, a large part of that maximization is being contributed by this number 4225. Whereas when you use 65 as the weight, only 2/3 around 0.66 is 2/3. So only 2/3 of that weight is being contributed. So what can you conclude from this? Okay, let's just, so maximizing D1 is almost like maximizing this, right? So that's 99% of the weight. Right. Maximizing this is fairer to the other one. So now, if your values are loosely packed, which one would you choose? Okay, I'll tell you. If your values are loosely packed, suppose you have a lot of values like 100, 200 or 300, what will happen? The largest value that you have, the number that is most distant from 35, that will contribute a lot of weight to capital. It will not be fair to the other numbers. So when your numbers are loosely packed, you will penalize less. Because when you penalize more, it becomes almost 99% of the weight. Faraway numbers will contribute more. The numbers that are in the middle will not contribute at all. So when your numbers are far apart, you penalize less. When your numbers are close, you penalize more. Should I repeat, or is there any question? Did you get it? Because if the numbers are close, you can penalize more. You can get by with penalizing more. Essentially. Because even the farthest point is not very far away. But when you penalize more and your distances are far apart, your points are very far apart, your entire objective function, this capital D would be called an objective function, the entire objective function would be constituted by those faraway points.
When the numbers are loosely packed, penalizing less is understood. But when the numbers are closely packed, why should we penalize more? The same thing is going to happen. Even within the small range, a particular number will be there which will contribute more. So,
that's because how the quadratic function behaves. You see, when you have a small range, it doesn't really matter.
So that is something. It doesn't matter. So can we say it distinctively? Should we penalize more or should we penalize less? We're indifferent if the numbers are close.
Even if we penalize less, nothing bad is going to happen.
Right.
That is fine. But we penalize more, that's kind of custom. Or you can say that we penalize more because there are other factors. Solely from this, we can't say that we should penalize more, but there are other factors. But even if you penalize more or less when your values are closely packed, it doesn't really make a very big difference. So now when we are convinced that these distance metrics should change, the location measures will change automatically. For example, we've all heard of the median. We've all heard of the median as a sorting tool, as a sorting operation. It's not necessarily a sorting operation. We choose this distance metric, d of xy is modulus x minus y. We follow the same procedure. In fact, first you can check that this value distance is less trivial. So you choose this distance metric and you follow the same procedure. So let's first. So this is essentially the same thing that I had there. So I choose my basic point as 30 and I see the distance of point 30 to 40, which is of course 100 because it's 30 minus 40. But the same point is not that far away, so I choose this distance metric. It's just at a distance of 10. And of course, both of them are symmetric, so you get the same values. But for far away points, you can see it goes up to 4,900. And if you had a value like 4,900 in your objective function and the other values were like 100, your entire maximization would be concentrated on this one. Whereas there it would be, it is just 7 times. Whereas here it is 49 times. So distance is essentially like that's the idea that you can choose distances. Just like you can choose distances in real life. You choose distances in numbers as well. And this is actually how horrible the difference is. So what I've done is I just took the same exercise that I took earlier. I took my basic point as 30. Took all numbers between 0 to 60. And over this range I applied my d, which is the squared one. And I applied the absolute distance function. And then I plotted square distances on range. Just familiar syntax. The other thing is, when you already have a plot, the blue line, I already drew the blue line, then I wanted to add a green line. So instead of saying plot again, I say line this time. Because if I say plot again, then it will delete the previous. So simply say line. Then I say delete. And look at the difference actually. The green line looks like a horizontal line. That's how vast the difference is. They of course converge on 30 because at 30 they both have to be 0. But at say 0, the square distance is far, far away, and this is probably not even crossed 100. So these penalties do make a difference. And in fact, you can't see the difference here at all. So what I did was I took a smaller range, say 28 to 32. And when I took a smaller range, then you can see. Then you can see actually a special feature here that when points are very close, the absolute distance gives a higher penalty. The absolute distances give a higher penalty when points are close. Because you don't expect points to be close. So essentially the penalty is for what you consider unnatural. When you don't expect points to be close, you give them a higher penalty because you consider that unnatural. And when you have points which are far apart, if you consider that unnatural, then you use the quadratic. So whatever you consider unnatural, you give that a higher penalty. Whatever you consider natural, you give that a low penalty. So with absolute distances, I consider points which are near very unusual. So I give that a high penalty. And with quadratic things, I expect points that are very far apart to be unusual. So I give them a high penalty. First, we can get back to that same slide. Sure. again that same three-step procedure. You start with a D. You suppose that your location measure is mu. Calculate distances, aggregate them. Same thing we'll do for the median as well. So I'll come to the Lake Huron because there is a special feature that you can't see in Lake Huron. This is another software called GNU plot. Just quick and dirty plotting, that's what I'm using it for. So what I did was I took 3 points. One point is at 30, another point is at 35, and another point is at 40. And what I did was I said that double multiplication symbol is for exponentiation. So this is the absolute, this is the square distance that you already saw. So I say plot f of x, and we already know that the mean will be somewhere around 35, and that's what it comes out to. Okay. Now absolute distances work differently. So the median will also be 35 actually, but the way it gets there is quite different. When you use absolute distances, you no longer have a continuous, the differentiable function. You have breaks. So at 30 you have a break, at 35 you have a break, and at 40 you have a break. It looks different. But when you have a large data set, it looks roughly similar. So we had a whole Lake Huron thing. You can't see it there because there are 98 points there. But it's not the same thing. You have breaks there. On the same graph, you have breaks there. And I've made 2 because otherwise they would overlap so much that you won't have been able to see. But there are breaks. So the absolute distances work. In this example, the mean and the median almost converges. But the way that you get there is good. Now, we have the mean and the median, and they sometimes come down to the same thing. So when does it matter? Perfectly behaved data, what I mean is essentially normally distributed data. And normal distribution is a very, very tame distribution. Essentially, you are saying that no matter how much I multiply it by, the expectation will still exist. Normal distribution is not simply symmetric distribution. Normal distribution also says that expectation of x to the power k, no matter how high k may be 1 million, but that expectation will still exist. So it's a very, very tame distribution. In fact, you generally don't find normally distributed data. No data is normally distributed. So for normally distributed data, of course, the mean and median converges, but there is no perfectly behaved data. So should we stop or should I can stop. Okay, I'll continue. If you want me to stop, I will stop.
Could you work on R and syntax for a while?
Okay, what do you want to ask?
Basics of R and how to...
There's nothing really complicated about it. The syntax is just like C. Ask me something then.
Like how to comment, how to import data, how to assign libraries.
Libraries is just is the library. And yes, we can say that gives you
How to assign a directory?
assign a directory. What do you? Okay, you can set a working directory.
You save in a particular place.
I can set. Always say set WD and you can say save.
How do you find something specific from this one?
You can always say that. You can
say for the nature of the data.
you can say
Can you put extended resources to the section like percentile, first percentile, 99th percentile?
see that's the difference between R and I mean you can get it. I'll just come to it. I'll just tell you the guiding principle. So the idea behind R is that it will give you exactly what you ask for. It will not give you anything else. So when you say summary, it's not actually summary. This is 2 keys 5 point summary. So yeah, of course you can get the context. There's no problem in it. But you can't get long output like SAS gives you. And then you say what quantiles you want. So for example, if you want the first percentile, to give you exactly what you ask for, it will not give you anything else. You can get the deciles also, for example. I mean, you can get just without anything. You just have to frame the question. So I use my sequence function. So I use my sequence function to go from 0 to 1 in 0.1 intervals. That gives me the percentile. Deciles.
So what does this give you?
Gives me the deciles. I go from 0 to 1 in 0.1 intervals.
Oh, I see. Okay. So here if you can basically do what you want with this.
This is a vector. In fact, you can store it. This is a vector. You can store it. So physics. Each time it will return you something. I mean, it doesn't give you just output. Everything that it gives you, you can use it further.
How to save the statistics in a report format, say in HTML format or Word?
You can do that. The best way to do it is SSV, basically. You can do it. There are packages for that. There is R2HTML and so on, essentially. But the principle will be the same. The way that you write those documents also will be the same. The idea of doing it in HV or this kind of stuff is that suppose I do it the way you do it. I copy this and I paste this in some Word document. Why should the other person trust me that these are the contents? There's no reason to trust me. I can always change any of these values. So the idea behind SVF is something called reproducible research. That I should give my code and my data exactly to the other person and he should be able to replicate it. Otherwise I have no reason to trust any figure in any data. Everything else is, if you don't share your data and if you don't share your code, the research is useless because it's just something that you see. There's no reason why I should accept it. So with S3, that is fine.
So how do you use the SVF?
S3 I won't use here. What I would do essentially is I would write my LaTeX document and somewhere in that LaTeX document, wherever I want to do something, I'll do these things. And the advantage of using these, this is actually a name. First assignment is a name.
This works with any tech editor.
No, it will work with any tech editor. You write a document like that. Then you go into R and you say, I deleted it. You basically call SV on that. because this file doesn't exist, so it will not work. So you call SV on that. Once you call SV on that, it will output a file, and that file will look something like this. And in fact, you don't actually have to look at that file because it will just have results like this. You don't actually have to look at that file at all. Whatever you want, you do in the RNW document. Pass it through R, pass it through PDF, and you get the PDF. There's another idea behind it. It's called literate analysis or literate programming. The idea is that when you look at, these are called code chunks. Things like these are called code chunks. Actually, each of these is a chunk. Whenever I put these and this, I suppose this is basically the chunk. Actually. And I can give it a name, first assignment, or I can give it any name I want to. The idea is that I can actually, if I give this thing to it, I need not write everything that I want in sequence. I can actually number them. So for example, I can write x squared, and I can write x minus 30 later. X is 30 later. I can actually do that. And the advantage of that is that you no longer have to follow the same linear way. For example, if you are writing in C, your first 5 or 10 lines will be simply variable declaration. You can actually put them later. You can write it. In fact, you can. This works with C also. This works with anything. It actually, the technology is actually novel. The technology is called novel, and the R implementation of it is called SV. So novel works with any programming language. You can mix any two programming languages. Any questions? Yeah. Stop it.
Could you share all these files and...
Sure. Because उसमें लेबलिंग में से मैंने कॉपी पेस्ट कर दिया So whatever you type is immediately evaluated. So when you say make you run, it's immediately evaluated. You can't do that, but it's not even recommended. What do you get from looking at this? No, even for these 98 figures, what do you get from looking at this? That's the idea. Graphs are always recommended. You can't look at figures and find out anything. I mean, just looking at them, this is just 98 numbers. What do you get from it?
Mohit? I just wanted to say thanks for today's session.